Off we go. This is a slightly whimsical piece. A little while ago, I looked at one of the artist's impressions of a red dwarf star, which is particularly red, and I thought, a red dwarf star is really as red as that. I can't remember actually knowingly ever observing a red dwarf star because they're pretty faint. So I thought, well, I'll have a look into this sort of a bit light-heartedly and see what I can come up with. Now, red dwarf stars, although you're hard pushed to actually find one and observe one in the night sky, it's reckoned that they make up something like 70% of all the stars in the known universe, as it were, which is really quite remarkable. Most of the stars that we see are sort of big and bright, but they're actually few in number in proportion to the number of red dwarf stars. This is displaying it graphically in a different way. This histogram. Here we have the class M stars, which is what the red dwarf stars are part of. These are the definitely reddish stars. You can see this nice red bar here. They do straddle somewhat between the K and M boundary, but mostly they're in the M stars, which are regarded as red stars. You know, this is the OBAF GKM sequence, so we have the supposedly bluish stars at one end, or blue, and red stars at the other. Of course, we never see any green stars, and the reason for that is quite simple, because you're not dealing with simple very small discrete areas of the visible spectrum. You're dealing with a lot of wavelengths mixed together, which produce a somewhat desaturated version of the supposed colour. You'd be hard put to find stars of these deepish blue colours here, or indeed find stars of such a brilliant red at the other end of the spectrum. Now, here's the main sequence in diagrammatic form. These are the so-called dwarf stars running all the way down here. You can see that the sun is supposedly in the middle, supposedly a yellow star. And as you get down to the cooler end, it drops off very rapidly down here. The reason it drops off so quickly is that the luminosity drops off. Remember, the other axis as against temperature is luminosity. As the temperature falls, the luminosity of these small stars drops dramatically, and that's why they sort of tumble off towards the bottom end of the spectrum there. And as I said, you don't find stars which are as red as that, or as blue as this, or indeed as red as this. Not really. So there's a matter of or almost aesthetics here, you might say. So the Hertzsprung-Russell diagram is, in a sense, a desire to cover the full visible colour spectrum between deepish blue and a deepish red, even if that doesn't quite tally with nature. What is colour? Now, physicists and philosophers will doubtless argue about this forever. But ultimately, we have to ask the question, which the ancients themselves probably asked: does colour really exist out in the world, or is it simply a matter of perception? Now, here we have some representative wavelengths of light and the colours which go along with them. 460 nanometers, definitely blue. 660, definitely red. Now, these are sort of discrete emissions, bear in mind, you don't get green stars. And the question is, how much of this perception of colour is out there in the world, and how much of it is inside the brain, as it were? It's likely that this is down to very deep and probably shared physiology between most life forms on this earth that can perceive light, but they're not exactly the same, of course. And there's no obvious reason why the brains of ourselves and indeed other animals shouldn't assign different perceived colours to these wavelengths. Why not have a 460 nanometer red, or a 660 nanometer green, for instance? But that is, of course, not what we actually see. Now, this depends in part upon the actual detectors which are in use, in this case, the human eye and its cone photoreceptors. But of course, these days we have CCDs and CMOS detectors as the successors to film. Now, all of these have their particular peculiarities. All of them have their failings in one area or another in perceiving and recording colour. Now, this is my cat, Fluffy. Now, I don't I don't know what colours he sees in the world. I really don't. I dare say if I asked him, he wouldn't tell me, but he can be like that sometimes. And the human eye is our primary receptor, of course, for our particular species. But I'm going to define colour here as the conscious perception of detected wavelengths of electromagnetic emission, with the emphasis on the conscious perception there. And as I've already mentioned, no sensor is perfect, whatever that might mean, but it serves its own function. They all have their plus and minus points. Now, we like to define colours in a sort of extreme sense. I don't think any of us would argue, if we have normal colour vision, that the dress on the left is quite a deep red colour, and the one on the right is a deep blue colour. These are almost what a photographer or an artist might call as spectral colours. That is, if you isolated a little bit of the visible spectrum and discounted all the other colours, you might get colours as pure as this. But do any stars have these colours? No, not in reality, in terms of perception. But we also like to push it to an extreme in how we describe colours. Now, the dress on the right is blue, but what would you say the colour of this stone is on the left? Now, this is called a blue stone. It's somewhat similar to the blue stones that you get at Stonehenge. Here in Lincolnshire, these things were deposited by the last glaciation about 12,000 years ago. This is actually outside the museum in Louth, quite close to here, and it's what's called a glacial erratic. It doesn't belong here. Particularly if it's a wet weather, it does tend to look a bit more bluish. At the red end, here's the red dress on the left, and here is old red sandstone on the right. But would you really describe it as red in comparison to the one on the left? A sort of reddy brown colour, but that's about as red as rocks themselves naturally become. What colour would you say this is? Well, technically, I suppose you could call it a cyan colour. I have constant arguments with my wife when we see a colour like this, and I will say that it's more greenish than blue, and she will say, oh no, it's more bluish than green. And I have wondered, is there a gender difference, a sex difference between humans, whether men and women see these sort of colours slightly differently? I have no information on that. And of course, the brain is a funny thing. It tries to create what we call colour constancy. If you like, the brain knows what colour things should be, and it presents them to our conscious mind accordingly. So, you get used to, for instance, incandescent light in a room, and you think, well, it's putting out white light, but you take a photograph of it, and it's yellowish to slightly orange light. But the brain interprets it and presents it in terms of consciousness as being what it expects to find. What colour is our sun? I've already mentioned that it's in the middle of the Hertzsprung-Russell diagram, and it's referred to as a yellow star, which is a bit odd, really, because how do we define the colour white? The colour white, as our brain interprets it, can really only come from the integrated light from our local star, which is the sun, and it doesn't present itself to our conscious minds as being yellow at all. There it is again in the middle, in the sort of yellowish part of the spectrum. But what if you take a photograph of it? Now, this looks like a black and white image of the sun. It's not. It's a colour image taken at a high quality observatory, and there's no fiddling around with the colour to make it look yellowish or red, or whatever colour you want. It's just a straight integrated light colour of the sun according to that particular detector, which has received the light upon its surface. Of course, you can make a star look redder by adding extra material. This was a photograph I took about 3 or 4 years ago, really, when we had another blast of Saharan dust, and it got into the atmosphere and turned the sun remarkably red on that particular day. And of course, this happens with stars as well. You can get red stars called carbon stars, which, as the name suggests, Their atmospheres are full of cooled and condensed carbonaceous or carbon materials, which effectively remove the bluer component of the light, such as they have, from the light being emitted, and makes them even redder than they would otherwise appear to be if that carbon wasn't present. And right down at this bottom right end, here we go through the white dwarfs. You can see here the M areas of the spectrum. And we're talking here, notice 2500 kelvins. That is about the midpoint for red dwarf star surface temperatures. But they come down here from about 3000 Kelvin, and by the time they got to about 2000 Kelvin, they're off the red dwarf scale, as you might say. So it drops off very rapidly as the luminosity drops. And then when you get down to this region here, you're into the carbon star region. Very dim, but also very red. And they are given spectroscopic codes all of their own. So here we're talking about, well, four things really: colour temperature, black body radiation, Wien's law, and the Stefan Boltzmann constant. I'm not going to go into details here, obviously, because it's not a physics thing and I'm not a physicist. Colour temperature is a term which is normally used by photographers or artists. It's the colour which they would expect to see from a black body radiating at a particular temperature. So that, for instance, if you have what we call a blue-white star, then obviously that has a very high colour temperature and it emits a certain colour as we perceive it. And we can regard it as essentially a black body radiating. Wien's law comes into play with the actual amount, that the spread of the radiation through the spectrum of the emitter. It needn't be a star, could be a tungsten lamp or whatever it be. And this goes according to the temperature of the emitting body, this hypothetical black body. And as the temperature drops, more and more of the radiation is emitted towards the redder end of the spectrum, and indeed off into the infrared, the invisible infrared. The Stefan Boltzmann constant refers to the actual luminosity of the glowing black body. And this states that if you vary the temperature, the actual luminosity, the amount of radiation emitted, varies according to the fourth power of that change in temperature. So that if you double the temperature of the surface of the emitting body, the actual amount of radiation the luminosity, total luminosity, goes up by 16 times. It doesn't double, it goes up by 16 times. Equal, if you halve the temperature of the emitting surface, the amount of the luminosity goes down to 1/16 of what it was before. And so here we have a continuous spectrum for different bodies, different temperatures of emitting body. The blue star up here around 12,000 Kelvin, you can see that it peaks in the bluish area of the spectrum. It still has a full range of visible wavelengths, and it tails off as it gets into the redder end and the infrared area of the spectrum. Here, the sun, roughly 5,000 or 5,500 Kelvin, you can see that it peaks in this area, so you can perhaps understand what's referred to as a yellow star, but it has all the rest of this visible spectrum mixed in to produce what we call white light, and it gradually tails off again into the red. But when we get down into the red dwarf area, which starts at around 3,000 kelvins, yes, it still emits in the visible, but a great deal it peaks in the red, which you might expect, but a great deal of its light is not visible to our human receptors, our eyeballs, because it's in the infrared area. But there's rather a lot of it in comparison to the amount in the visible part of the spectrum. Looking at something which is a bit more familiar, tungsten halogen lamp, an incandescent lamp, this is the region of the red dwarf, so you ignore the sort of colour coding for the purposes of the diagram. But 3,300 Kelvin is just a bit warmer, hotter than a red dwarf would be. You can see how the spectrum is distributed. This is the visible part, but already down at 3,300 Kelvin, A great deal, more than half of the emission is down into the infrared part of the spectrum. And if we drop down to this area here, 2500, 2000 kelvins, these bottom two lines, you can see that a very small proportion is actually in the visible and most of it is in the infrared. Here's another diagram, an incandescent lamp at the lower end of red dwarf temperature, 2200 Kelvin. Only a little bit is emitted in the visible part of the spectrum. A big hump around 1500 nanometers, and almost all of it, the emission, is in the infrared part of the spectrum. Colour temperature, as I say, this is a term which is not so much used by physicists, more used by photographers and artists. But you can see the spread. Candlelight clocks in at about 1800 kelvins, and we go through the sort of red dwarf area. But notice that at a blue sky, such as we've had this past couple of days, is in the range of 8,000 to 12,000 kelvins. Now you might say, well, that's odd, because the sun is creating this light, and so it's just a version of sunlight, which it is. But it's sunlight with the blue light coming into the detector, and all the rest of it not coming into the detector. The blue sky, the molecules of the atmosphere scatter the blue component of sunlight around very easily. So if you're not looking directly towards the sun or measuring direct sunlight, the light from a blue sky would actually be the same as a black body surface radiating at this very high temperature. You get a similar effect on snow in sunlight, particularly if you look at the shadows created in the snow. They can take on this bluish cast. And a high colour temperature doesn't always mean a high temperature source. You can of course get radiation, visible radiation from ionized sources and fluorescence and that kind of thing. So I decided I'd do some little experiments to see what results I could get by varying the temperature of various things. In the old days, if you wanted to warmth in the winter and you didn't have a coal fire, you might have one of these, a so-called electric fire, which is not on fire at all, but it's just heated metal wire heated up to a particular temperature, and you can see it gives off a lot of heat, not a great deal of light, and it's rather orange red in temperature on the right hand side there. But its temperature would be considerably lower than the surface temperature of a red dwarf. Here's a maniac in America who likes building go-karts of various descriptions with pulse jet and ramjet engines, and you can see here they get up to fair old temperature. But this temperature here, which looks white hot, is really only an artifact of the camera sensor being overexposed. So it ends up showing white rather than the actual colour. And at lower temperatures here, we get this red-orange. Now this is still at a higher temperature than the red dwarf, but it's not so much as to melt the steel. Sorry, I'll go back to that now. I'm gibbering. This area of emission here is a lower temperature than the red dwarf. If it was at red dwarf temperature, it would probably be melting the steel. But you can see we've still got this sort of quite brighter orangey red, even though it's significantly lower temperature than the red dwarf. Sorry about that. Anyway, a tungsten light bulb in a clear glass bulb. Here's what it looks like. This is a photograph which again is overexposed, so the filament looks white purely because the sensor is receiving too much of this incoming radiation and it cannot record it as the actual colour. You can see here in the background the reflection of that filament off the glass at the back of the bulb, and that gives you a rather better idea of what the actual temperature of the glowing filament would be if you could perceive it without overexposure. Now here what I'm doing, I'm passing a 10-stop neutral density filter in front of that filament, so it's reducing the light output by 1,000 times, and as you saw there, it looked that particular yellow colour. But what I'm doing now is actually reducing the current to the filament, stepping down the voltage and stepping down therefore the temperature, and you can see we went down and we're going down through the orange into the sort of reddish area of the spectrum until it more or less disappears from view, bringing up the temperature back up by increasing the voltage, and we get back up through the yellow part until it's overexposed on the sensor once again. Now, that was a tungsten lamp with more or less a thin wire filament. This is what they call a sort of antique version of a tungsten lamp, and this has more of a tape filament rather than a wire filament. And again, if I put the 10-stop neutral density filter in front of the lens, you can see that it is actually a yellow colour when it's not actually overexposed. Now, the temperature that we've got here is not really all that high. It's probably not far in excess of 2000 kelvins for this sort of antique type of filament, but it still looks yellow. But that is considerably lower than the temperature of most red dwarf stars. Now, what I'm doing here is not using the filter, but I'm reducing the exposure in camera to make sure that it isn't overexposed. And if I drop the exposure really down, I get again this sort of yellowish colour of the filament, which is more true to life. Now, if I take that a filament and reduce it down in the camera in terms of exposure, but then artificially brighten it again on the computer, you can see that we're back up to that yellow colour. Now, this is the temperature of the filaments. Now, if I reduce the voltage of through that filament, we get a decidedly, I think hopefully you can see it, a reddish filament glow here. If I take that particular image, which I've made the filament distinctly cooler than its normal operating temperature, and I brighten it artificially on the computer, yes, now we are into the really reddish area. But the temperature of the filament that we're looking at here is probably not very much in excess of 1000 Kelvin, 1000 maybe to 1500 Kelvin, which is considerably cooler than a red dwarf star surface temperature. And I might ask, do red dwarfs indeed have a single colour? Well, I've said that there's a range taken as the range of red dwarf stars, which is rather arbitrary, to be honest, between 3000 and 2000 kelvins, but they are also prone to flaring. They can throw out really energetic flares, and presumably these are hotter and brighter than the rest of the star. So the actual colour of the star overall will vary over time, depending on how active that particular star is. Here's a typical red dwarf star as imaged by Hubble. These are 623b. I don't know what the actual temperature of this is, but it's probably around the mid 2500s or so Kelvin. But it's a reasonably orange-red star, and you can see the colour, as we see, varies according to the degree of exposure by the sensors. When they're overexposed in the middle, where it's gone to white, over on the outside you get a much more reddish coloration. So I was simply saying, in conclusion, really, that red dwarf stars are not all as red as they're often painted, and if you do a little bit of experimenting, they often rather more orange than red. But to remind you that they still make up about 70% of the stars in the known universe by our estimates, and they're also here for a very, very long time. This is solar mass on the bottom. If you can see, if you get a star which is a quarter of a solar mass, and I should say that red dwarf stars are defined as kicking in at about 0.1, 1/10 of a solar mass. At the quarter of a solar mass, they're around for somewhat less than 1 trillion years. But if you get into the red dwarf area proper, you can see 6 to 7 trillion years is where they start. By the time you got to the lower end of the red dwarf spectrum, they might be here for in excess of 10 trillion years. In other words, every red dwarf star which has come into existence is still around, which can't be said for a lot of the much bigger and brighter stars. Are there any redder stars? Well, yes, I mentioned the carbon stars, which are a bit like cloudy red dwarfs. They're even smaller in size and lower in mass, and their outer areas are so cool that carbon-containing compounds actually condense out absorb what little blue is that there is in the emitted spectrum from the red dwarf stars, and it presents us to our views as a particularly reddish kind of stars. So there we are. That's my little whimsical piece on red dwarf stars. If you ever manage to actually see one and photograph one, I think you should let us know. Anyway, I shall stop sharing there.
Many thanks, Ray.
Okay. It's supposed to start. Oh, there we are. Yeah. Okay.
Does anyone have? Could we have perhaps one or two questions for Ray?
Can I have one, please?
Yeah. Go on, Bud.
Ray, thank you very much for this. I've always wondered why you can't see green stars, and you explained it really well. Now, my question is about photographers. Often you hear photographers describe light on a picture as being cold when it actually is on the blue side, and being warm when it's actually on the orange side. And I wonder why that is.
Well, that's partly an aesthetic thing, and partly it's how our perception of heat really. If you're out in a bright, cold, crisp day with a clear blue sky in Finland or whatever, the light is bluish, but it's distinctly cold. Whereas if you were standing in front of a glowing bar of electric fire, it's distinctly warm, even though the actual colour temperature is much lower. So it's a physiological thing, really. It's how we perceive heat on the surface of our bodies. And leaning over into the aesthetic side, because of this, if you see a light colour which is reddish or sort of yellowish, orangish looking, even though there is no heat involved, we still describe it as a warm colour because we are associated with that warmth of emission from a heat emitting source. That's all. So you can get a blue source of light, like a blue LED, for example, and it's, if you touch it, it's not going to freeze your finger end off. It's just that we associate it aesthetically with the colours which we have become used to as we've evolved and played around with materials and lit fires, etc. So it's a perceptual stroke aesthetic thing, really.
Thank you.
Anyone else like to ask a question?
But yeah,
Okay.
Ray, I could. You talked about the people perception of blue and bluey greeny, and
Yeah,
the exact opposite. When I see something as blue, she sees it as more greeny.
yeah.
So I think there's certainly a difference from human to human, whether it's sex based or not.
Yeah, you would have thought somebody would have done research. They probably have research on this. I've not seen anything definitive about it, but there does seem to be, certainly, as you say, differences between people. Quite how you work this through. I mean, how do you know that you are seeing the same colour as somebody else? Well, you can't know. Not until we can share consciousnesses between people, which hopefully will never happen. So, we live in the world together, and what we perceive as colours are presumably sufficiently close to each other that we can get by and make choices. But it's like trying to agree on the shade of paint for a wall or whatever. You might never agree because you perceive it slightly differently. Yeah.
Could be that there is a gender difference. I mean, my wife sees more green in the
Yeah.
green things, and I see more blue.
Yeah.
So that's three people with wives who
Yeah.
see
Yeah.
green, and
Yeah.
we see blue.
Yeah. Perhaps we should do some research.
I like your green jumper, James.
Yes. Yeah.
Good one.
We'll have a break. I suggest something like 10 minutes or a bit more.
I'm going to ask another question of Ray about red dwarfs. Why do red dwarfs appear to have enormous outbursts like you showed in one of the diagrams, where more so than sort of normal, well, non-red dwarfs, I would say.
Yeah, I can't say very much on that. Perhaps we ought to do a part B on the actual astrophysics of red dwarfs. It's all down to the magnetic fields again. But why such a small star and relatively cool star should create such enormous local magnetic fields? I don't know, unless Robin has anything to add. I'd have to work on that one, I'm afraid. Yeah. I'm not sure it's very well understood, to be honest.
I might well read that myself.
Yeah.
I'm sorry, but it looks like time has beaten us. We've got to stop the meeting here.